Hi folks, and welcome. This video we will be looking into the use of Python, or more specifically control systems library of Python, for plotting pole zero map and step response of an example second order system. We'll also print out some relevant parameters such as peaking time, percent overshoot using Python. The second order system that we will look into is a system that we had already looked at during our lectures. It is this system here. The transfer function of the system is given as 5 over s squared plus 3s plus 4. We had done some calculations by hand to figure out, for example, the settling time, percent overshoot, steady state gain, as well as the peaking time. Let's see now if Python will give us similar results. Just as a disclaimer, this is not an introduction to Python as such. If you are not very comfortable with Python scripting, then I'd suggest that you look into some introductory Python videos on the web. So let's start. I'm using an IDE called Spider. You don't have to use an IDE as such. You can just type everything that we're typing here into a text file and run the script. Save the file, of course, in a directory of your choice with a .py extension, and then run the file through your command line using a command that looks like this. In your whatever your directory is, you can write Python and then script.py, the name of the script, whatever it is, and its extension. And that's going to be sufficient. Now let's start and let's look at what we need to do to be able to plot, for example, pole zero map and step response of the second order system that I just showed you. First of all, before we do anything, we need to import the necessary libraries. One of them is called NumPy, and when you import that, import NumPy as np. Press enter. Next, we import another library called matplotlib .pyplot as plt. This is going to give us some visualization capabilities, such as plotting a 2D graph, right? So we import that too, and then finally we have to import the control library. Here we can write import control and enter. Before we do anything, obviously first we have to tell Python what the transfer function is. We do that by defining a new variable, g equals control, referring back to the control library, and we will call a function from the control library. So we type a dot, and the function name is tf. Open and close parentheses. So now we have to define our transfer function here. We will have two more entries, and we'll have the entries in these brackets here, square brackets, comma, another one. These are called as Python lists. Right now they're empty. Here we will enter the coefficients of the transfer function. First of all, the numerator. Second of all, the denominator. Let's start doing that. So in the numerator we had 5, and in the denominator we had 1, 3, and 4. If we go back to our function and have a look at it, you will see that the coefficient for the numerator, you can imagine that we have an s to the power of 0 here, which is not written. It's 5, and in the denominator we have an s squared, and coefficient is just 1. We have an s, coefficient 3, and we have 4, s to the power of 0, which is not written here. That's the last coefficient, right? So, all right, let's go back. Once we have written this, we can press enter, and let's see if we have entered everything correctly. So we type print, open parenthesis, and g, and close parenthesis, and press enter. So this will print the transfer function as defined through the control.tf function. As you can see, this is the output of the print g call, 5 over s squared plus 3s plus 4. It seems to be correct. Now, before we do anything more, let's open up an empty figure, plt.figure, and then in parenthesis 1, I just give the figure itself a label, and plt is referring back to the matplotlib.pyplot library, and figure is just a function defined in that library, and that's going to give us an empty window, basically, which we will fill now with the, first of all, the pole zero map. Let's do that. And that's pretty straightforward. We just call the control library itself and dot another function from the control library. It's called pzmap. It stands for pole zero map. And as an argument, we give the g, the transfer function itself. This will already plot the pole zero map. As you can see, it's a second order system with no zeros and a complex conjugate poles. Both poles are on the left hand side or the left half plane, so the system is stable. Let's put also a grid in the plot so that it's easier to see things a little bit, or it's a bit clearer to see where the poles, where the pole locations are in the plot. All right, this is done. We have our pole zero map. And the next thing we will do is to calculate the step response of this system. To do that, we define two new variables, t and y. T stands for time, and y is basically the values of the step response, the numerical values, which we will plot later on. So to calculate the step response, again, we need to refer back to the control systems library, control dot another function, step underscore response. All right, now we open parentheses. Now the only argument we will give this function right now will be the transfer function itself, g, and then we close parentheses and then press enter. This doesn't do anything, it won't plot anything as such, but it calculates the step response. Now when we're calculating, when we're plotting the step response, we also want to plot the unit step input. This is calculating the unit step response of the system. Now we would like to plot also the unit step input, so we'll define a new variable, step underscore input, and then we refer to the numpy library, because this is going to be a one-dimensional array filled just with ones, so np.ones. This declares a one-dimensional numpy array, so-called numpy array, and fills it up with just ones, nothing else, and the length of that array should be the same as the length of time array that the step response function gives us from the control library. All right, so now let's define another figure, another window, another empty figure, which is now created here right above the pole zero map. All right, so now we'll start plotting, nothing else. But then we refer back to the matplotlib.pyplot library as plt dot, and the function is just called plot. Here we will just give the x and y values, which will be just t and y that we defined just now. And now let's give it a label also in quotes, as let's call it the step response simply. This is just a label for the data points. This will be plotting the step response of the transfer function gs that we have defined. Do that. Now we see that the blue curve here shows the step response of the system. The x-axis here is the time given in seconds, and the y-axis is the value of the function itself, or the step response of the system. All right, let's also plot the in the same figure, but then we use the same function plt.plot the step input. All right, let's give it another label. Let's call it just step input. Now this is going to plot the step input, which is the red curve, or just a straight line basically, as its unit step input. So, all right. Let's also define grid here because it makes things a little bit nicer, I think. Yes. All right. So now let's also include a legend in the figure so that we see what the blue curve means, which is the step response, and the red curve is the step input. All right. Let's also define the x and y axis labels. X label, as I mentioned, it is time given in seconds, and the y label is just the value of the function itself, ct, let's call it. So now everything is in place. We have the step input, we have the step response, we have the axis labels, and yeah, it all looks good so far. One last thing we will do is to print basically some of the relevant parameters, as I said. Let's and compare to our values that we calculated by hand. To be able to do that, let's write print statement again, and in parentheses here now we will refer back to the control systems library. Control dot, there's another function there called step info underscore step underscore info, which will have an argument too, and its argument will be the transfer function itself. This will print the relevant parameters such as peaking time, overshoot, etc. for this system. And press enter. Yes, as you can see, this prints the rise time and its numerical value, the settling time, its numerical value, settling minimum, its numerical value, etc., etc. So let's look at some of the two of the relevant parameters that we are interested in. Is the, let's say, the overshoot, 2.837, etc. This is given in percent, although it's not stated anywhere there. It's given in percent. If you look at our calculated percent overshoot that we did calculate during the lectures, we calculated a percent overshoot of 2.8%. So this is corresponding well with the values estimated by using Python. Let's look at the peaking time. The value is about 2.37 seconds. The unit is here given in seconds. This is the same for settling time. It's also given in seconds. Rise time, it's also given in seconds, etc. The peaking time is 2.37 seconds, estimated by calculated by using Python. Let's have a look at our hand calculated value, which is going to be 2.37 seconds, which is good. The steady state value that we calculated is 1.25. This is the value we calculated by hand. I guess Python gives us also, let's see, if we look at the value, steady state value of 1.25. Yes. So everything seems to be in order. All right. So one more thing that I should mention, if you do not use an IDE such as the one I'm using here, and if you want to have everything in a text file and then run through your command line, there's one more command that you need to add to be able to plot actually the step response and pole zero map. That is plt.show open and close parentheses without an argument in the parentheses. There is no argument. This is basically needed. Otherwise, if you lack this and then you run this, you run a script through your command line, you won't see any figures popping up in your screen. So you need to tell Python to actually show the figures, that the two figures that we had plotted here. All right, and that's all there is to this. This is how basically you can use Python, and specifically the control systems library, to plot to calculate the step response of a first order, second order, or nth order system.